Okay, here we go. So last time we were talking about change of variables, and let me just remind you what the big picture strategy is. We haven't actually gotten to the method yet, but the big picture strategy is we're going to try to generalize to a multivariable setting the idea of the substitution rule, which again I know y'all have seen before. I know y'all remember. Very quick reminder of what the big picture strategy is going to be. We already talked about this last time, but the big picture strategy is going to be to take our change of variables function that we previously thought of as just being kind of an algebraic thing, a thing that you plug in for x, right? We're going to view that as actually being an actual function where we actually take points from an actual domain and get outputs in an actual target, right? So we're going to think of this more sort of geometrically, as it were. With this idea in mind, there are two big points that we want to take in sort of understanding, how does the substitution rule make sense in this context, from this geometric point of view. One is the idea of the stretching factor. This thing, g prime of t, that's what you have to multiply by your input size, right, to get your output size. How much does this change a variable? How much does this substitution rule function stretch things out in moving them from the domain to the target? That's one of the big ideas. How much does the domain get stretched? Right? The other is this idea of a pullback, and a pullback is just kind of the big picture of what's going on here. That we start with an integral defined on a domain, right? And by creating this change of variables, I keep saying change of variables, it's morally a change of variables, but by doing this substitution, by creating this function g, well, that's what we use for plugging in purposes. That's what allows us to turn x into g of t. That's what allows us to compute the stretching factor and therefore reevaluate dx as something there. So while the function pushes points forward, right, that very same function takes expressions backwards, right? So just a casual parlance, we think of it as the function pushes points forward, but it pulls expressions backwards. I hope that kind of somewhat satisfying linguistically. Okay, all right, so with all of this in mind, let's just do now the same thing in a multivariable setting. Here we go. Same idea for double integrals. Right now we're going to start off presuming that we have a function. This is what we're going to call a change of variables function. This method that we're about to employ is called the method of change of variables. That function, again, we're going to think of as having a domain and a target. We're going to think of specifically that we're looking at a particular, I guess I'll say domain within the domain of the function. Domain for an integral within a domain for the function. So we're going to look at this rectangle. We're going to, fingers crossed, hope that it ends up being a rectangle. And it's going to have an image over here. When you plug in these light blue points into the function, well, then a bunch of dark blue points come out, and it's not probably going to be a rectangle. We wouldn't expect anyway. It's possible, it might be, but it doesn't have to be, and it probably isn't. Okay, so that being the case with this setup, all of the same ideas employed. Suppose that we find ourselves interested, I guess I should keep that color. Suppose I find myself interested in this domain. I'm interested in particular in doing an integral on that domain. I'm not happy about this, right? Look at this domain. It's terrible. Oh my gosh, if I slice this way, I'm going to hit that corner and that corner. If I slice this way, something weird's going to happen down here on the bottom for one thing. Then I'm going to hit that corner, then that corner, then that corner. Ugh, right? So this is not a good integral to be having to deal with, at least not directly. So the big idea, though, then is, well, yeah, but if that domain is itself an image of a change of variables function, then can't I just take these outputs, x comma y? Can't I just rewrite x comma y as g of u comma v? That's what it is. That's what x and y are. They are literally the outputs from this g function. So g of uv is x comma y. Nothing happened there, really. I'm just plugging in, right? The only thing that's really sort of interesting, you might say, the only thing that's non-trivial, is that I do have to figure out, okay, well, how much area that doesn't really go well color-wise. Okay, let's see, how much, what would be a good color choice there? Man, I don't think any good, let me try yellow. All right, that looks kind of yellow. This little piece of area here, that little piece of area, it's not the same as this little piece of area that led to it. Again, this change of variables function stretches things out in the same way that this interval is not necessarily the same size as that interval, because this function might stretch things out. Likewise here. This little piece of area, not the same as that piece of area over here. Whatever it is, we're going to have to figure out a formula for how to compute this. But this piece of area that I have called dA should be something times this little piece of area du dv. There should be some sort of a stretching factor. So notice we find ourselves in the same situation. We're still, again, looking for a stretching factor. How much does this function now stretch out areas? Right? And secondly, notice again, there's a pullback happening. I started with an expression, namely an integral, defined on the right. And by the action of plugging in, I'm pulling it back. I'm turning it into an expression defined on the left. Right? So same two big ideas. All right. Now, so the good news is that there is a convenient formula for this stretching factor. Let's see, I don't think I can quite fit this all on. We'll do it like that. This stretching factor, I'll use green. That stretching factor right there. Good news, nice easy formula. Here it is. It's the absolute value of the determinant of the derivative matrix. And I know myself well enough to know I'm going to slip up occasionally and call this the Jacobian matrix. That's what they called it when the class that I took as a young college student. Jacobian determinant, common expression for this thing. But I'm going to try to stick with the book's convention. This is the absolute value of the determinant of the derivative matrix. Why is it that expression? Is a topic that I'm going to delay for a bit because there's enough going on as it is, and I want to get to let's get a couple of wins under our belt first. Let's actually get some dirt under the fingernails, actually do one, kind of get a sense for how this looks and how this feels, and then after that we're going to come back and I'm going to talk about where that formula comes from. Quick reminder, don't forget what the derivative matrix is. It's the matrix of partials. Arranged in that very particular way. Do make sure to get that right. Second thing I want to talk about is another little point of notation. The determinant of that derivative matrix is sometimes shorthanded like this. Partial xy over partial uv. Probably kind of see some of the motivation for that. I mean, a casual sort of like sloppy take on what this says would be, look, I'm taking the partials of x and y with respect to u and v, right? And that's what you see inside of this matrix. Of course, now very importantly though, this fraction seeming thing is actually not the matrix, it's the determinant of the matrix. That's important. Also very importantly, and you've heard me say this a bunch of times, this thing here, this partial xy over partial uv, looks like a fraction. Absolutely not. It's definitely not a fraction. You can see right here, it's defined as a determinant. Determinants aren't fractions. Right? We write it as a fraction because what we're going to find is that it actually kind of behaves like a fraction. But cannot emphasize this enough, it's not actually a fraction. Now let me try to persuade you in what sense it kind of behaves like a fraction. And I'm going to come over here and rewrite what I've got in this expression here, looking at how this is equal to that. And let's see here. Our stretching factor, keep in mind, is partial xy, partial uv. Don't forget your absolute values. There's your stretching factor. Times du dv. And look how nice this is. Now again, this is totally illegal. This is a math crime I'm about to commit. So this isn't real, and don't believe it, but look how convenient. As a memory tool, it's like those cancel, right? And as a memory tool, as a way of keeping it straight, wait a minute, which way does it go? It always goes in the order in which this faux nonsense cancellation would appear to work out. And notice that what is left over there, it would seem to track with the idea that it represents a piece of area in the xy plane. So again, don't believe it, but it is a convenient little trick, and I find it very handy. Okay, all right, so that's why we write it as a fraction. Again, it's because in this way it behaves like a fraction. Okay, how are we doing? Is everybody with me? I'm going to do an example right now. Here we go. So we have, now this is, by the way, is a very manufactured example, deliberately manufactured to be maximum convenient. They won't always be this maximum convenient, but we want a nice, easy one to start with. So here we go. My integral that I wanted to be in highlighter mode. My integral that I'm going to be interested in is defined on this region right here. And again, let's take a moment to recognize what an extremely undesirable integral this is. In a couple of different ways, by the way. One in particular, though, is when you start slicing this up, you're going to hit two corners. Whichever way you slice. Right? So that's no good. Nobody wants to do that. That's three separate iterated integrals. Also, notice that on each one of these curves, if I look, for example, on this curve right there, I need a relationship between x and y to describe that curve. I don't have a relationship between x and y. X is given to be this expression, and y is given to be this expression, but it's not immediately clear what the relationship is between those expressions. So that's another problem, right? It's going to be really hard to find the bounds if I look at this integral as is. Okay. All right, so there's my integral. I'm going to use change of variables. Now, how am I going to use change of variables? Keep in mind, per our setup over here, I need to arrange it to where, let me get rid of my mess. I need to arrange it to where the output domain, right, needs to be literally the image of the input domain. Right? So I'm going to have to figure out specifically how to make the domain I've been given, how to make that the image of something I like better. And now that's why I say this is a highly manufactured example. In this example, it is explicitly given that my domain here, right, my domain for my given integral is the image. So how often is that going to happen for you? Maybe not super often. It's not unheard of, but not to be expected, and we'll talk later about how to deal with it if that's not, in the very routine examples where that's not the case. But it's the image by way of this function of the unit square and the UV plane. Okay, so we're in business. We have everything we need. Our undesirable domain is literally an image of a more desirable domain. I have my change of variables function explicitly given to me. Again, this is manufactured. This is not how it goes down in general. And now we're just going to apply this formula right here. Going to compute our stretching factor and pull back, which basically means plug in. Okay, so all right, let's compute that stretching factor. Okay, the stretching factor comes from looking at the function. First thing I have to do is I have to compute the Jacobian determinant, right? The determinant of the derivative matrix. Now, there's a little bit of legwork here. You've got to take your x formula, right, and take its partials with respect to u and v, and you got to take your y formula and take its partials with respect to u and v, right? Now, do make sure, again, I remind you, to make sure you remember the structure of the derivative matrix, and it's really easy to accidentally get your columns and rows reversed. You want to make sure you don't do that. We take the determinant per the formula, and our Jacobian determinant ends up being this expression right here. Great, fine. Nothing to it. Except here's the thing. Our stretching factor is actually the absolute value of that. So my actual stretching factor is the absolute value of 4uv minus 9. And so I'm not happy about this because when it comes to actually doing the integral, keep in mind my big goal here is going to be to take my original undesirable integral, to pull it back, thus giving me a new integral, and then of course I'm going to need to compute that new integral, and I don't want there to be absolute values in there because none of the shortcut formulas, none of the antiderivative rules that we know allow you to take integrals that have absolute values in them. Right? So this is not good. So how do we deal with this absolute value? There is a surprisingly convenient way to handle this that works very often. And that is to just remember, you've got a picture right here showing you what u and v are doing. And I can see from this picture, right, my pullback domain in particular is this square. That was given in the statement of the question. And check it out, u is always between 0 and 1. Right there in the picture. And then likewise, v, well, there's my v-axis. V I can see as well. On my domain that I actually care about, right, on this domain there, v is always between 0 and 1. And now I can just at a glance look at this expression and say, well, u and v are always between 0 and 1. 4uv, therefore, is always less than 4. 4uv minus 9 is therefore always less than negative 5. That means it's always negative. And if you take the absolute value of something that's always negative, the absolute value is the negative of that negative value. Does that make sense? It's a good one to think through. If a number is negative, its absolute value is its negative. How are we doing? Okay, well, it's all over at this point. It's all over but the shouting. Just start plugging stuff in. I am going to zoom out so I can get all of this on the screen here. Here was our original integral. Oh, gosh. Let's see here. Yeah, our original integral right here. We do the pullback. Now, the first thing I have to worry about is what's the domain? Well, my domain in the pullback is that unit square. Again, as given in the statement of the question. Again, this is highly manufactured, deliberately convenient. Right? Okay, what is x? Really easy to lose track of what x is. X is one of the output coordinates of my change of variables function. It's right here in the formula for my change of variables function. So x is already known. That's just a matter of recopying, plugging in explicitly. Likewise, y, right? I mean, so y is this second output coordinate. Y is that business right there. So again, plug that in. Yeah. Don't forget your stretching factor, right? This stretching factor that we just went to this trouble to compute goes right there per the formula on the previous page, and we're in business. We've got ourselves a new integral to compute, and much easier than what we started off with. Now, I want to remind you, a lot of students will look at this and say, given my choice between these two integrals, I kind of like the one on the left, right? Mistake. The one on the left is defined on this horrifying domain that you're going to have to figure out how to slice up. And you are going to hit corners, and you're going to have algebraic nightmares trying to find the bounds because those curves are just not given in a way that's easy to work with. This is a sneak attack landmine integral. It's really hard. This one here's got a few terms in it, I suppose, but they're all polynomials. These terms are easy. Yeah, there's like 4 of them. But whatever, right? And the domain is awesome. The domain is mine, and I think very likely yours, favorite domain for a double integral. Just a unit square, constant bounds, hard to beat. How we doing? Okay. All right, so big win. That's our first change of variables. All right, moving along. Now, again, manufactured example, right? It just happened to be in this example, again, goal in mind of getting a win under our belt, right? Seeing how the mechanics flows. The change of variables function was given, right? The pullback domain was given. That won't be the case, generally speaking. In question. So how do you kind of do this in general? And you have to kind of tailor your approach to the situation. There is no, algorithmic process here. These are some change of variables functions that I think are particularly useful. Translations, stretches, and rotations. And keep in mind that, of course, what we're doing is, these are pushed forwards, right? And what we're interested in is what does this do to the domain? And, of course, what happens to the domain comes from pulling back. So in some sense, the opposite happens to the domain. And you'll see this in action in the next example. I'm going to do an example specifically of a rotation, and this will kind of counter-rotate my domain. Here we go, details. Suppose we are looking at this square. And that's going to be my domain for an integral. How do I compute this integral? Not given as an image. Change of variables function. TBD, right? We're going to have to figure that out for ourselves. Okay, so we're looking at this green domain here, this square. Clearly don't like it. Again, whichever way you slice, you're going to hit 2 corners, all else being equal. Prefer not to have to do that. Even still, those edges, now they're just lines, but they're lines where, they go through points where the coordinates are square roots sometimes, and that's going to be a weird 4 equations for the line. So, all else being equal, we're not excited about that either. Okay, so here's a big idea. This is an image. This is what you get when you rotate counterclockwise. Right? Specifically, when you rotate counterclockwise from this square here that I'm going to highlight in yellow, and then just because that is what goes into the function, and I like to put my domains on the left, I'm going to sort of redraw it there like that. So, in fact, let me get rid of the yellow on the right here. So what we have here is that my green square is a counterclockwise rotation of this easier square that I have on the left. Everybody on board? So this change of variables function is a counterclockwise rotation. Notice the upshot, though, is that I've taken my given green square and I figured out effectively how to rotate it clockwise to turn into my yellow pullback domain. Right? So I wanted to do a clockwise rotation of this green square, and I achieved that by realizing it as being a counterclockwise rotation of something else. How are we doing? Everybody happy? Okay, now some details to be worked out. Let's look at this counterclockwise rotation. This is all going to be Math219 linear algebra. Make sure you're good at this. Right? Rotations are linear transformations. Linear transformations are matrices. Matrices have columns that are the images of the standard basis vectors. Blah blah blah. Trig to figure out what those rotated vectors are, and formula. Right? Now, again, if you're still a little shaky on all that business, linear algebra was a long time ago, perhaps, and you've forgotten how that works, come to office hours. We'll be very happy to walk you through it and make sure that you're comfortable with how this works. But it is important that everybody gets good at this kind of thing here. Really valuable. And it will be assumed in this class. Okay, so then we compute the derivative matrix and take the determinant per the usual formula. And so that Jacobian determinant turns out to be 1. Now that's just details. Make sure you can do that, of course. Let's think about why that is. Is this, what a coincidence. Right? Does that make sense? Is this really, should that be 1? Yeah, absolutely. Of course it should. It's a rotation. When you rotate something, it doesn't change how big it is. So we shouldn't expect the rotated output areas to be any different than the original input areas. So in some sense, that answer better be 1. Now that said, even though it is geometrically expected, don't forget the purpose of any exam question that's about this is to make sure you can show me that. I want to see that you can do the calculation. So please do, on exams, on homework exercises, show the algebra. Don't make the geometric case. Is that yeah? Oh, okay. All right, yeah. Okay. Everybody good? All righty. So now it's just a matter of plugging in. Again, we started off with our integral on this undesirable domain up here. Oh, whoa, I just hit the wrong button. Sorry. Started off with an integral on this undesirable domain there. We're now pulling back to our new domain here. And so original integral on the undesirable domain turns into a new integral on my new pullback, squared off, parallel to the coordinate axes, regular convenient square domain. And in order to get the details to work out, again, don't forget, you got to plug in your stretching factor, which is the absolute value of that Jacobian determinant, absolute value of 1, which is 1. And don't forget to plug in the formulas for x and y. And those, again, are explicitly given in the change of variables function itself. This x right here, after all, is the first coordinate of the output, which is that dot product, which I therefore put right there. And likewise, this y, what is the deal with that y? If I'm rewriting everything in terms of u's and v's, that y, well, it's the second coordinate of my output for my change of variables function, which is this dot product right there. Cool. And again, now we're in business. And again, it looks like we've worked backwards. It looks like we've made things less good, right? Because this integrand looks at a casual glance easier than this integrand. But frankly, even the integrands, just barely. I mean, the only difference between these is that I guess I would say these constants are not quite as friendly looking constants. Right? That's micro point. The overwhelmingly more important point is that that domain is bad. And this domain is about as nice as they get. Everybody good? Yeah.
I feel like in single variable calculus we did this in order to modify the integrand, but here we're doing it to modify the domain.
Yes, that's a great point. Yeah, absolutely. Yeah, the motivation here is very largely about the domain. Yeah. And part of why that doesn't really show up in the single variable version substitution rule is that it's one-dimensional. There's not enough room for domains to get bad. So yeah, you're totally right. Yep. Yes.
Are we going to be expected to see the transformation ourselves?
Sometimes. Yeah. You definitely need to be prepared for that. And so I'm going to show you, various kind of standard-ish examples. I'm not going to ask you to come up with a change of variables motivated by a point of view that's completely unlike anything you've ever seen. That wouldn't be fair, right? So I won't do that. But so, for example, if I give you some shape that is a rotation of something nice, like this one, then totally, absolutely. And again, a couple other examples I'm going to show you. Yeah.
Should we know how to compose transformations?
Yes, because you can think of that in a couple different ways. You mean composing change of variables?
Like a rotation and a translation.
Yeah. I mean, sometimes you have to do that. Sometimes you have to rotate and then squish, and you can, you might motivate that by thinking of it as two separate transformations. But then when it comes time to actually do the change of variables, it's usually easier just to literally compose the transformations and then just do the change of variables once. But there's counterexamples to every rule. Sometimes you might literally want to do two change of variables. It might just work out more easily. Yeah, totally. Alrighty. Couple of things that have to get said. There is a regularity constraint here. In order for this to make any sense, we do need for the change of variables function to be continuously differentiable. Good news, it is going to be continuously differentiable in every example we're going to do. But just, point of order, that needs to get said. Also, it does always have to be invertible. And there's some weird things that can happen if your change of variables function is not invertible. And this is this is something that we just, in Math219, aren't going to have time to worry about. But nevertheless, it's there, so heads up. Let's see here. Erase. Okay. This next example is going to require a clever observation that I want to make before so that we can use it in the next example. Here's our original setup, change of variables function going this way, where x and y are functions of u and v. And forget about what we have down here. If I have a change of variables function that goes like this, then how much areas get stretched is this stretching factor, previously discussed, right? Oh, no problem. Okay. Let's see here. There we go. So this is that stretching factor. Okay, now, though, what if my change of variables function went the other way? Now, I'm going to make the observation that math doesn't really depend on arbitrary things like alphabetical order, right? And which way did you draw your picture, right? That's arbitrary conventions. The point to this blue stretching factor is that we're taking the partials of our outputs with respect to our inputs. That's the point for that stretching factor. So the same thing applies when we're going the other direction. We're taking partials of our outputs. The outputs of this green arrow are now u and v. And we're taking those partials with respect to the inputs of that green arrow, which are x and y. Right? So the stretching factor going the other way is this thing, partial uv, partial xy. And now I'm going to make a clever observation that, look, if I have some piece of area over here in the UV plane, some little piece of area, and if I were to take that and see what it turns into over here in the XY plane, and then see what that turns into back in the UV plane, well, it's going to turn right back into exactly what it had been. Right? So altogether, whatever area I have here, if I move over here and then come right back, I get the exact same thing. Right? Overall, then, this stretching factor going all the way around, overall that stretching factor is 1. Same output as input when you compose them together. And another way to interpret that is that this product of stretching factors is 1, and another way to interpret that, if a product is equal to 1, is that each is the reciprocal of the other. So neat fact, again, kind of satisfying. I think that if moving to the right makes things bigger, then moving back to the left should make things smaller. Right? Okay, by the same proportionality. Okay, so now this is another example, by the way, of these stretching factors behaving like fractions. I cannot emphasize enough, they're not fractions, right? This thing right here, this partial xy by itself, not a thing. A fraction, right, is a ratio of two things. That's not a thing. So again, please don't make the mistake of thinking that this result that I've got here in purple is obvious. It's really not, because these are not fractions. This is a statement about determinants. So non-trivial, but true. Okay. All right, so let's apply that to this next example. By the way, this next example is going to look arbitrary and manufactured, and it really isn't. And I want to let y'all know where I got this from. Well, this is an example that's in many multivariable calculus textbooks. But I first saw this in a physics course, right? In a course in thermodynamics. And a lot of y'all are engineers, are going to be taking a thermo class at some point. You're probably going to see certainly this picture, a picture that looks much like this. I've cleaned up the numbers a little bit for convenience. But you're going to see a picture that looks a lot like this when you're studying this thing called the Carnot cycle. And it's a very important theoretical construction that it helps with understanding certain things about how thermodynamics works. So anyway, very natural from a physics point of view. That said, suppose you want to do an integral defined on this region here, where that region is defined by, this is weird, a pair of curves here and a different pair of curves. Oh, let's see here. A different pair of curves like this. Right, so I have two pairs of curves that kind of intersect to make this weird, curvy quadrilateral. Everybody with me? Want to compute an integral over that thing. Now again, I guess you could start chopping in the usual way, but you're going to hit corners. Whichever way you slice, you're going to hit two corners. So this is, we really don't want to do it that way. It would be very unnecessarily tedious. So we want to view a different way of dealing with this integral. And this is a very clever trick I'm about to show you. I did not think of this on my own. I'm not expecting you to have thought of this on your own. I'm showing you the trick, right? And so this is one of those things, I used to get intimidated by stuff like this, where I think to myself, man, I never would have thought of that, right? You don't have to, right? I got intimidated for no reason. The person that showed me this, he didn't think of it either, right? So don't get too weirded out. here's the trick. It only works if your curves are written as level sets. Notice that's the case here. Each one of these 4 curves is a level set. That is critical to making this work. Next, notice that these 4 curves are level sets of 2 functions, right? Pairs of level sets of just 2 functions. That's also really important here, right? So I'll note if a question that you happen to be looking at, if they're not written as level sets, take that algebra that they've given you, right, and chuck it. That's not in the right form. You've got to rewrite those given equations as level sets first. Then second, identify these 2 functions whose level sets you're looking at. And then third, make those functions your u and your v. All right, so that's the tricky setup. And now let's celebrate how awesome this works out if you do that. Notice that gives me u and v as functions of x and y. So you can kind of see what's about to happen. My function's going the wrong way. We just got through establishing how you deal with it. If your function is going the wrong way, right, whatever you get for your stretching factor for your wrong way function, you're going to have to take the reciprocal. Right? So that's going to happen, but let's not worry about that for the moment. Let's think about the domain and what happens to my domain if I do this. We'll take this one little bit at a time. Let's start with this curve right here, xy equals 1. Okay, well that curve, xy equals 1, wait a second, that curve, if u is xy, then the curve xy equals 1 becomes just u equals 1, which is a straight line in the UV plane. Isn't that handy? Good news, right? So now you can kind of see why it was so important that these be level sets. I need equals a constant here, so I'll get equals a constant over here, which is what gives me a straight line. And then likewise for all the other curves. So let's take, I'm running out of colors. Let's take this one right here, xy squared equals 3. That curve right there, well, xy squared is what v is. So this is just v equals 3. Which again, straight line. Everybody happy? And so life is good. I mean, we've got a new domain. Again, having set things up very carefully and delicately, just so. My new domain, I get to get rid of this old domain. I get to use instead, again, a rectangle. Everybody's favorite. I do have to figure out the stretching factor, so I'm going to take the partials of u and v with respect to x and y. Fine. That gives me this stretching factor. Again, the wrong way. That's not the stretching factor I need. I need the stretching factor going the other direction. So don't forget to take that and take its reciprocal. The stretching factor I need is the one going that way. Which, by the way, if you get confused as to, wait a minute, how do I know it goes that way and not the other way? Remember, the algebra, the notation keeps track of this for you. Right? We started off with an integral dx dy. Oh, see, I forgot what I used for my colors. Okay, fine. I started off with dx dy. So whatever I put in here, if I'm trying to turn this into a du dv integral, per my setup on the previous page, and I need the result to be dx dy, what is the thing, right? What stretching factor would this need to be to make the bogus cancellation look good, right? To make it seemingly fit, nonsensically, but conveniently in that way that'll always put you in the right direction. And in order to make this cancellation work, of course, I'd need to have the u's and v's on the bottom. And thus I need partial xy, partial uv. Is that good? All right. So as per the previous page, you plug that in, and now notice I have a new integral. It's defined on my new domain. U and V range over that rectangle. So those are the bounds, and everything great except for the one little annoying detail that I need this now written in terms of U's and V's, and I don't have it written in terms of U's and V's. And this is an unavoidable algebraic consequence of going the wrong way. I can't change my mind and say, okay, I'm just going to turn this function around. Very often, usually I would say, the whole reason that you go the other way is because going the wrong way is significantly more convenient in many examples. I'm aware that, of course, in this case I could get clever and I could turn it around. But the point to this example is to show you how to deal in this circumstance. So here's the big idea. If you find yourself with an integrand that you need to rewrite in terms of U's and V's, that's what U is, and that's what V is, make a guess. The guess won't always be the same. The guess is going to depend on the nature of the circumstance. So let me walk you through where I came up with my guess here. I have a product of powers of x and y. This is specific to this circumstance. A product of powers of x and y. Then I need to rewrite in terms of u and v, each of which is a product of powers of x and y. And now here's the question that we face. What should I do to products of powers of x and y to produce a product of powers of x and y? And I think it's reasonable to suspect and hope, at least, that I would take a product of powers of products of powers to produce a product of powers. Now, again, that's just kind of wishful thinking. There's details to be worked out. But the reason that I speculate the purple is based on what the blue and the orange and the green look like, right? I mean, would I expect my purple move here to involve cotangent? No. Why? It just doesn't. No, you just look at what you've got and think what's gonna likely make things fit. You can then take these equations and go through and you can solve for your A and your B, and thus rewrite that in terms of U's and V's. So it's always going to be different, but you want to make your guess what your relationship's going to be. You want to make your guess based on the existing forms that you're looking at. Okay. All right. So let's see here. We have a couple minutes left. I think that'll be perfect to just kind of circle back on where all this came from in the first place. I promised I'd give you an argument for why the stretching factor is what it is. What we have here is a picture of a piece of the pullback domain, which, when you plug it into the change of variables function, will get stretched out in various ways and produce typically something that's approximately a parallelogram in the original given push-forward domain. Right? So what I want to do is talk about what's the relationship between the green area and the blue area. And this is actually a very straightforward thing. Just make sure to remember that these edge vectors, we know exactly what they are. That one there that I have in green, it's in the E1 direction. This is a little square of width du and height dv. So this horizontal one is E1 du. Right? Now, I want to know what happens to that to produce this output vector. And remember, we have a pat understanding of what you do to input vectors to produce output vectors. The output vector is what you get when you apply to the input vector the derivative matrix. The derivative matrix turns input vectors into output vectors. So conveniently, notice that what that means is that I now have an explicit formula for one of my edges of my parallelogram that I'm interested in. And of course, if you want to understand volume, area, the area of a parallelogram is a determinant of a matrix whose columns are the two edge vectors. So what we see here, we've directly computed this first edge vector, and then I'm going to say analogously the same deal. That second edge vector is that. And it's kind of all over at this point. A couple of algebraic observations to make. One is that constants like du will factor right out. Likewise, dv factors right out. Now, we look at this determinant right here. Well, actually, let's just look at this matrix right here. Real clever observation. What can I say about this matrix? Let's look at its first column. The first column of this green matrix, dg times E1. Wait a minute, what happens when you multiply a matrix times a standard basis vector, old linear algebra fact? Matrix times standard basis vector gives you the corresponding column of that matrix. So what I have in blue here, this is the first column of dg. Okay, let me say that again. The first column of the matrix I'm trying to understand is the first column of dg. Likewise, the second column of the matrix I'm trying to understand, this second column is the second column of dg. So this matrix that I'm trying to understand is dg. Clever little linear algebra observation there. And so there you go. There's your stretching factor right here, the stretching factor. You see, ultimately, that stretching factor comes out of our existing formula for the area of a parallelogram, and you see now we have that which I multiply by input area to get output area, and done. So let's call it a week, and we'll pick up here on Monday. Y'all have a good weekend. See you later. And by the way, stick around just for a moment. Make sure I get you marked properly on attendance. I think I have most people, but just in case.